Okay.
Okay. Can we start over?
So yes, the mission was just to check whether some list together with all lists inside it are empty. But of course, this isn't really well defined because lists are potentially in Python can be defined or can contain themselves. So if you have a list that contains itself, it is a list defined, let's say L. It is an object that is defined in terms of L. And not only is it defined in terms of L, but you cannot really answer the question whether L is completely empty without answering the question for all its constituents, including, of course, L. Of course, it's not necessary. For example, this list is, of course, not completely empty since it really contains a number 5. So it really doesn't matter whether what is L here. But in this case, you cannot really answer the question because there is not a single model of lists who have very precise and fixed values, so that you can see whether such a list is empty or not, right? Of course, you can write a program, but it will be recursive, and this recursion will not end. The really similar situation we get with numbers. If you have a number defined in terms of other numbers, of course, it is easy to check any property of it that you can check. But if you have a number that is defined in terms of itself, then it might be hard. You might be having to solve some equation or something like that to determine the property. And those equations really don't need to have a solution, or they can have many solutions. So we are again in a similar situation to this one. Of course, this is not so theoretic. You can in Python really construct a list. Here I have L is an empty list, and I define and I append L to itself. And of course, Python can even write out that list for me, of course, using the ellipsis, because it cannot really write out all those lists inside themselves. But you can access any item. Of course, L length of L is well defined, and it is 1. You can access index 0, and it is a list, and you can access index 0 of it, and it is a list. And of course, you can do it any number of times you need, and you will never get any list except L, because of course L is the only element of L. So however you can write some trivial recursive function. For example, whether a number is odd, and you can say, for example, if n is less than 2, then return whether n is 1, else return whether n minus 2 is odd. And you can, of course, ask whether 2 plus 3 is odd. Man's not defined. Oh, right. And it will say true, of course. But you cannot really ask Python any of these questions, because Python does not have a way to define a number in terms of itself. And it is very connected to the fact that numbers, integers in Python are immutable, while lists are mutable. So the only reason we were able to define this L in terms of itself, you see, here we have defined L, and it was empty, and after it we have changed it by referring to this L, and of course now L is something else, and L was mutated to contain itself. So it doesn't really matter whether the object contains anything or not. The numbers and lists differ on that plan, but not only that. I mean, not really that. but whether something is mutable, because the only way you can refer to the object after it is created is by its name, and after the creation, of course, the object, if it's immutable, then you cannot really put it inside itself. We have objects that are very similar to lists, but they are immutable, they are tuples, so you cannot do this. You can try to say something like this, but now you cannot really put L inside L. You cannot say this, because of course tuple does not have an attribute append, and it is really a nice exercise to check that really there is no way, there is no method on L that you can call that you can such that you can get a tuple that contains itself, and it is by design. It is very a very precise because of course L must be hashable, so you can calculate the hash of L. Of course, it depends on the members of L, so you cannot say hash of. You can calculate hash of I don't know, a pair of 2 and 3, and it depends on some way, some XOR or something like that. Depends on the hashes of 2 and 3 of its elements. So of course, if you somehow made a tuple that contained itself, its hash would be recursive in the same sense and wouldn't finish. Of course, you cannot really hash any list, whether empty list or some other list, because lists are unhashable. So they're really different from the perspective of this property, and of course that means that one of them is not appropriate for this task and the other is. So
why I'm not sure. So the only reason why list is not unhashable is because of there is possibility for making a link on itself, or why?
No, it is one of the reasons, but it is not the only reason. The big reason, the main reason is that lists are mutable. So why are hashes needed? Hashes are needed if you want to construct, for example, a set or a dictionary or something that you are not really concerned with the order or the number of some elements. You are just concerned with the property whether something is in there or it is not. So you must check containment in a fast way. Of course, there are many ways in computer science to do this. You can always just put your elements in a list, and you can check whether something is in a list. Of course, in Python it's perfectly doable. But of course, if this list has 1 million elements, then you must check. If the element is not there, you must check all the 1 million of them. And if the element is there, you must check on average 500,000 of them. And it is a big job to do. Of course, you can do much more easily if you, for example, if you sort that list. If that list is sorted, then you don't really need to check all of them. You just need to use binary search. Python has binary search in the module bisect. Oh, wait a minute. I had the order wrong, probably. Yes. So what did I get? I got an index of, but not really an index, but the index where I should insert the value so it is in sorted order. You have bisect left if you need a real index, if the element is there. So you have a bisection, and of course, if a list has 1 million elements, then 20 probes are okay. But how does it do it? Of course, if the list is sorted, it must contain the elements of the same or comparable types, and the type must be comparable also with itself. There are types that are not comparable with itself. The most famous are complex numbers. right? You cannot say whether one j is smaller or greater than 2j because they're both imaginary and not real. So you cannot really say, you cannot really sort a list containing complex numbers, because you will see Python will tell you that complex numbers are unorderable. But of course, you don't need to do this. You can put all various things in your list. You can put some functions. You can put the sorted function itself. You can put tuples. You can put strings and various other things. And of course, sorted will still not be able to sort it, because they're really different types. For example, this int is in Python 3, it is a type, and the sorted is really a built-in function or method, and cannot be compared. So the sorted really is not the way to do it if you need to check of various types. But you can, there are no problems with making a set of int sorted pair or a string. You can make such a set, and you can I don't know how to refer the previous answer, but here, okay, you can check this. How does it do it? It doesn't do linear search, of course, and it doesn't do bisection. It does hashing. So it hashes this function. It gets some number, and it just sees whether that number is in a list of hashes that are here. So, for example, okay, the implementation is not really that simple, but it has some number of buckets. For example, there are 8 buckets. And this hash, when it is calculated, it is divided by 8. So, and you get a number. You get a bucket where it might be contained. Of course, there might be others with the same reminder when divided the hash by 8, but if there are enough buckets, the probability is small. So when you want to see whether sorted is in there, you don't need to look at all of them. You just need to look at the right bucket. Okay, but for this algorithm to work, it must be it is essential that the hash doesn't change. So if, for example, if Python allowed you to do to put lists in set, to hash lists, then you might be able to do this. Of course, it doesn't allow you, but let's pretend for a moment that it does. Then you might do this. A is an empty list. Okay. Now I construct a set with A as an element. Of course, as I say, it won't allow me to do this. But let's suppose I just say I append something to the A. Okay. So now A is the same list, but it doesn't have the same elements. Of course, you can check the ID. Of course, let's say here. Okay. So here, and now append 6, and now I can ask if Python were able to allow me to construct such a set. I can ask whether A is in S. Of course, the question doesn't really make sense, because A is the same list. So if I'm concerned with the identity of an object, A is of course an element of S, because S was constructed.
It wasn't. This is what S wasn't defined because of the construction problem.
Python doesn't allow me to do it, but I'm trying to explain why because otherwise it would be in a contradiction with itself. It would answer that A is not an element of S, or that A is an element of S, but both of these things would be unacceptable, because if I make another list, B, now A is the same list that it was before, okay?
Okay.
But B is not. ID of B is something different. So A and B are different objects.
Yes.
They contain the same element. What should the B in S answer? Of course, here the answer is opposite. If you are concerned with the object identity, then the answer must be no, because B is not A.
But I'm concerned. Okay.
And if you are concerned with the values, with the object inside of it,
that S is even defined. Are you trying to put what is S right now? Because S is not defined.
S is nothing. S is mathematically impossible object. I'm trying just to tell you why hashing is important and why lists are not hashable.
I'm just wondering why then it says name error, not hash error or something.
Of course, because this statement was never executed.
Okay,
it was executed, but it didn't produce anything, because this raised type error. So the assignment was never done.
Yeah. Okay.
Okay. So I'm just trying to, by a mathematical contradiction, to show you that it is really impossible to put a list in a set.
Okay.
Because lists have values, have elements in them, and they have their identities as objects. And those are fundamentally different. But containers are usually concerned with just the values of elements, and hashes really cannot take this into account, because lists can change their elements all the time. So if you have hash of A is something, of course it is now impossible to do it, but if you append something to A, and then again ask whether hash of A is the same, and in some view, in some branch of logical thinking, it must be the same number, because A is the same object. You haven't rebound A to something else. And on the other hand, it must be different, because A has now different elements. And it really doesn't make sense. Okay, so let's do this. For example, I say A is an empty list. Okay. And B is a list containing 6.
Okay.
Now suppose I make a set containing A and B.
Yeah.
And ask what is the length of this set.
Okay.
Of course, it is 2. Those are 2 different objects. But after I append 6 to the A,
yeah, that should say 1. But
you see, it's completely impossible.
That makes sense.
Cardinality of S cannot change if I just append an element to a list of it inside it. Okay. Yes. Okay. So what was the problem? The problem was that lists can be recursive. They can refer to themselves. So I tried to completely mathematically characterize well-founded objects. So those are the ones where you cannot really phenomena. But there was still some interesting problems. For example, of course, this is mathematical characterization. You have an idea of well-founded sets. I think Wikipedia will be of some help, or well-founded relation, whatever. Practically a mathematical definition. Okay, it is not really what I was looking for. Okay, not not really what I had in mind. Well, but really, the idea is simple. The idea is that you cannot have a descending chain of infinitely many objects inside. Of course, the easiest way to have an infinite chain is to have a chain of the same object. So you can have X that is in X, and of course now X in X in X in X is an infinite chain. But you can theoretically have infinitely many objects that you generate on the spot with some generator or something like this that are different, and they really form such a descending infinite chain. However, Python is really interesting in that regard because there are strings. Of course, if you have a, I don't know, tuple or have a tuple. Then, of course, you can have 2 is in 2, 3, 4, and 2, 3, 4 is in T, and it works. But you cannot really, maximal depth of this in is 2. You can have a tuple with greater one. For example, you can put 3 and 4 inside another tuple, or you can put something else here. But still, it is a finite depth. So you can have, for example, 5.
You change it to Markdown. You should copy paste it. Or yeah, yes. Just in the next.
Yes. Okay, but still, once you have a concrete tuple, you have a finite depth. There are no these in chains which are greater than 1, 2, 3, 4.
Okay.
But in strings you can, because there is an empty string and it is in an empty string. So you can have. Right. So it is really an infinite chain, and of course, immutability is not really the right criteria, because strings are immutable, but they have some other weird notions about containment, such that this doesn't really apply. So I really tried to pin down those examples and define precisely mathematically. Still, there were some counter examples, such as one that Stefan Pochmann found. I think that in the meantime, yes, it was fixed. So it is well founded and well sized. What is well sized? Well founded is that you cannot do in depth. You cannot go in infinite depth, and well sized is that you cannot go in infinite width, because of course you can have a generator that, for example, repeat is famous for that. It produces something that's empty, for example, an empty tuple. And of course, the depth of such error is 1, because you cannot really have yes, because nothing is inside empty tuple, and only empty tuples are in error. But you can have this infinitely many times. Every time you call the next value, you get the empty tuple. Of course, you can Of course. So just 10 empty tuples, and you can have as many of them as you want, because repeat just produces new ones whenever you need them. So of course it's not only necessary to be unable to go in infinite depth. You must also be unable to go in infinite width. And when you put all those conditions, then you can really make an algorithm for it. Without those conditions, of course, you cannot make an argument, because the question is really not well defined, as I showed. And so of course there are interesting solutions, but almost all of them are doing the same thing. They are just recursively checking whether all of the elements inside are empty. For example, this is the top one, which is just the canonical way to do it, I would say. They just differ in the ways of checking whether something should be checked for emptiness, or or it shouldn't be checked inside. It is really just a number, for example, or something like that. Let's just. Yes, nothing is said about this. So you can try to check whether something is iterable by checking an abstract base class. There is such a thing in Python, but it doesn't really work in the precise meaning of the word iterable. It was in fact no. It was in fact reported as a bug, but the people, core developers, said it is not really a bug, because abstract base classes were never meant to capture the all of Python's protocols in their full generality. So, for example, oh yes, I am searching at the wrong place. Collections, ABC. Oh yes, so it is iterable, and it just says it is ABC for classes that provides the iter method. But there are some things in Python, or even if there aren't, you could define them, that doesn't define an iter method, and still it is an iterable by some other protocol, maybe older one. So the only real to do it would be to check with try except. So you can just try to iterate through it, for example, with map, or with a for loop if you wanted to write a statement. But if it raises an exception, of course, this is an empty except, and it's not necessary. You know what exception is going to rise. If it's not iterable, it is a type error. So it should really be except type error. But of course, Stefan looks at every character and shaves it off if it's not necessary. So he just wrote an empty except. And of course, if anytime it comes to this, of course, the answer is false, because it means that iterable contains something that is not in itself empty, but it rises a type error when you try to iterate through it. So it contains something that is not uniterable. So it is by definition not completely empty. And if it works, if the map works, if it is iterable, then you just map completely empty over value, and you see whether the map yields for every value inside whether it is completely empty by recursively calling this function, and all, of course, checks whether all of them are true. And it also checks it in a smart way. So if it finds a value that is false, it doesn't check anything else. So you can, in fact, have something that is not well sized, which is of length infinity, but at the start or at some finite index to have something that is, for example, a number 5, and it will still work and it will respond 5. Infinite, it will respond false because it will just check until that. Of course, if you don't, if you have such a weird object such as this R, of course it will not work because it will just see whether the empty tuple is empty all the time, and of course every time the answer will be true. But it doesn't really have to work here because it is not well sized. It was actually Stefan's counterexample to the first formulation of my task. Okay, so of course, as I said, there are other types of solution, but they mostly differ only in the ways of trying to assert whether something is iterable. I don't know. Not really available to conclude for the yes. So if it is iterable, of course, then it must have checked for in a special way, but not really necessary, because if the string is in there, it is not well founded in that sense. Of course, I really think that. So what if this check was not here? I think it would still work. Yes, of course, because if you see, I haven't actually defined f. F is not really whatever it is. It doesn't really iterate at all because it knows that this one is empty, right? But of course, so you can write false here. It will still work. But of course, as soon as it is not empty, it will give you false. So this is really not needed. Okay. So this is all about it that I wanted to say. Some other mission?
Yeah, which the domino chain identify block there.
Well, let's look at domino chain. It is a nice way of really checking whether someone has the skills of both the programmer and the mathematician, because it really is a this problem is able to be modeled mathematically. It just, as I said, I don't know if it's here. No, it's somewhere else. The comment of mine that just says you are just counting something that's called Eulerian paths in a graph, right? So if you okay, maybe some clarification is needed. For example, if you have these tiles, you can just okay. So now I need to draw something. Let's the most elementary possible tool. So I will just no. Where's my brush? Okay. So you have the numbers, the possible numbers on dominoes. Of course, it is possible to have dominoes with greater numbers, but let's say that only 1 to 6 are are there, and then you have some dominoes there. Of course, for example, now you have 1, 5. That really means that you have an edge between those two, and you have 2, 5, and 3, 5. And you have 4, 5, and 3, 4. 4, 5, and 3, 4. So now you're just trying to build a path that passes through all of these edges, to each of them exactly once. So, for example, you can go from 1 to 5, to 4, to 3, to 5, to 2, and it's really it is this one. Okay, do you understand?
I forgot to turn on.
Hello?
Yeah, I think.
So you just see how many paths are here that pass through all of these bridges. For example, you can imagine them as islands and bridges over them. And of course, there are two mathematically dual problems. One is Hamilton's problem, which says that you must visit every island, and Euler-Euler problem that says you must visit every bridge. In this case, you must visit every bridge, each of them exactly once. So, for example, when children are asking, for example, can you draw a house in this particular sense or in this particular sense with only one stroke, without lifting a pen from the paper? It is the same problem.
Okay.
Okay. But of course, this doesn't really ask only if you can, but how many ways you can do it. So you must count them, and it has some mathematical theory behind it, which is not really simple. Some of them are simple. For example, you must not have nodes of odd degree. For example, those two are of degree 3. It means they have 3 edges coming out of them. This one and this one too, and you must have only 2 of them. If you have more than 2 of them, then of course it is not possible, because each one of them must be either starting or an ending point. For example, if you have a square with the diagonals, then, for example, if you start here and then here, there is no way you can pass through this one, because you must go, for example, enter here and exit here, and there is no way to cover this bridge. Okay, so there are some mathematical ways of characterizing a number of edges that go out of some node, but in the end, since you really have to count them, you must write some recursive function. And here it becomes interesting, because when you are writing code to do it, you just write a recursive function. Of course, it is not very hard to do it. However, there is an interesting thing that can happen. You can have loops. You can have dominoes which are the same, right? For example, 3, 3. This corresponds to a bridge that goes like this. And what it does to your number of possible paths? It is very easy to see that I thought that it doubles them, but not really. It can with another number, but this number can easily be calculated. Let's just I think it is the top solution because of my thumbs, where I just wrote that comment, how easy it is to find discarding loops, right? So it is. Yes, so it writes this kind of recursive function, or of here not really recursion, but BFS. However, this. If you find some path, then you just multiply it with all the counts, how many times it contains a loop for every loop that is detected, and it detects loop at the beginning here. So loop is just a domino which has a same number on each side. So I really think it's not necessary to count, because I don't think that domino can have two dominoes with the same pair of numbers. So you cannot really have two of these. I think. I'm not really a domino player, but I think the domino set has only one such domino for each number, not more of them. But of course, this is easily generalized, so you just need to count them and multiply the solution. You have only 6 of them, 6 numbers, and you have a loop through each of a single loop for each of them. It is already 2. So each one of them multiplies the number of paths by 2. So you just 2 to the power of 6 is 64. You have 64 times as many paths as without those loops. 100 of them. With all those loops, you have 6,400. So especially in a recursive function, it is very great way to prune those tree of possibilities by just considering loops as special cases which just multiply the number of your paths with some number, not really having to consider them all. Okay. So it uses the right tool. It uses programming to handle graph traversal, so it uses just BFS, but only without loops. And after it just multiplies it with proper constants for each loop to handle the symmetry. And it is really nice.
Yeah, I haven't solved this mission. I haven't solved this mission, and I was expected that this solution is not that complex, actually. It's complicated.
Well, it doesn't really have to. The poster just wanted to be very clear, but of course you can write it in 3 lines, like this. I can try to.
It doesn't make it easier to understand. Yeah, but
wait a minute. I think I have a solution. I didn't publish it yet, but it is still.
You didn't
I'm still trying to write some things in more exotic ways, but you can see how it looks right now. So I just process the input string. That is really not necessary, but I guess the author of the mission thought it would be easier for him to write many tests for task if the input is a string. But of course, the input is really mathematically a set of pairs of numbers, so I convert it to a set of pairs of numbers in this line, and then I just write a recursive generator. So I think you have seen my yield from Explorer solution to Open Labyrinth.
Yield from Explorer.
Yes, I think you have given it some thumbs. It is a classical example of a recursive generator. You just write something that will generate all the chains, and of course, after you have such things, you cannot ask a length of it, but you can just iterate through it in a generator expression and sum the ones. It. So this just tells you how many objects are in your generator, and then you have to divide it by 2 because the task says that reflections do not count an inverted chain is not considered as unique. So each of them actually has two variants if you start from the beginning or if you start from end. So you just need to divide by 2. Of course, it would be interesting to see whether there is a palindrome, but there are no palindromes because each domino tile is unique. So you just need to divide by 2. And to generate all the chains, you just have to pick up the start domino, see what are numbers on it, A and B, and then try to start the chains from B and yield them, and only if A is different than B. Of course, if it is double domino, then you don't need to rotate it. But if it has different numbers, then you need to see all the chains that start with A and yield them too. And how do you figure out the starting chains? Then you have an additional parameter, the domino with which you have started, and this is the base case. If you have no more dominoes, then you have your path and it is empty, and otherwise you just iterate through all the dominoes and see whether it on the upper level it has the number that you start with, and if on the lower level it has the number that you start with. If, for example, A is start, then you just call yourself recursively and append, I mean, prepend this next domino to the start of the chain. Of course, then you can also start the chain with this domino, but you have to invert it, so it is not really next, but it is BA. And it is a recursive function that works. Of course, these two functions are very similar, and they can be written as just one function which has a number that a second argument that is none. So, but this is just a very, very clear and easy way to write a general algorithm for this. Of course, it is much more general because it finds all the chains instead of just counting them, but it might be easier to understand. Okay.
Okay. You haven't shared because you want to.
Actually, it's really not still finished. Of course, there is enormous application in those two functions. You might want to refactor it a bit, but if you want, I can publish it. But I'm already level 20, so I'm not really motivated to publish code anymore. Besides, everybody has seen it now, so what else needs to be done? Okay. What else? Oh yes, all those legendary string missions. So which one shall we? For example, no,
That's not.
No, those for double substring, for example. Whatever. I think it is. I think it was Stefan Pochmann that really showed how similar those solutions are, because he wrote one solution to rule them all. He just wrote 4 very, very similar functions and just called. 4 problems, 1 solution. I must show this. So you have the common boring part. You have a function that finds the longest substring of a string that satisfies some predicate. And now, just by changing this predicate and by changing the post-processing, he writes every solution.
Okay.
As one liner. Okay, so if you have, for example, let's take this as a black box. It's not really, it just reiterates through all the beginnings and all the ends and yields all the. Oh no, it doesn't really yield. It just
okay.
Figures out the longest one because it goes by reverse length. But let's just see how we can change predicate for each mission. So repeat inside is simply okay. This is not simple, but it is the one where you say that S is in doubled S and trimmed. So you, for example, if you have a okay, so this is actually not a syntax error. You have ABC. This is not true. But if you have a string that is repeated, that is doubled, for example, A, B, and B, so you get a doubled, and then you trim it, remove the first and the last character, and then you see that it is true. It really is. It really checks whether something is double, but it's not really easy to prove. But it's easy to show on some examples. So this checks whether the string is repeated inside itself. It is a repetition of some other string.
Yeah. So basically, he just go through all the strings and substrings, all the possibility, go through all the possibilities, and yeah.
This one, yes. This one just gives you the longest substring that satisfies some predicate, and this is a very interesting predicate that you can write as a lambda that checks whether some string is repeated within itself.
Yeah.
Okay. Okay. Non-repeat is very, very easy. Non-repeat just means that all the characters in such a substring are different. So length of S is the same of the length as the length of set of S. So if you discard duplicates and then you count them, you get the same result as when you count them without discarding duplicates. That just means that all of them are different. Okay?
Yeah.
Long repeat is really not, but of course this is not the solution for this mission. So
it's just we just released recently. Yeah, that's the bug. Yeah.
It is simply that there are at least two. There is more than one character inside.
Lower than, yeah. Okay.
Yes, the less than one or zero. Yes, it's possible to be zero because there is one test that says what is long repeat of empty strings. So of course there is some sense to say that the answer is zero because the answer is length of empty string. And this one, double substring, is also easy. You just have to count the occurrences inside of S inside line. There must be at least one of them, or S might be empty. Of course, it is also possible because if you have an empty string, Python will not count it for some interesting reason. Of course, I think it was also reported. No, it will count it. Oh yes, but it will not count it many times because, of course, it will not be greater than zero, greater than one because it is one. But this really is. I think it is a bug. If it's not a serious bug, but it is very weird. Why should an empty string be only once inside empty string? I can very honestly say that I see 3 empty things here. You see.
You mean the Python bug? Or...
Yes, I think it should be handled more nicely. For example, you could answer that you could argue that the answer is 0 because really there is nothing inside empty string, so
okay.
There is not even an empty string there. You could answer really.
That's interesting.
Infinity. Python has infinity without problem. So you can say that this is the answer. You can I think the clearest would be just to trace value error, because if you're trying to count some substring in a string, it's more complicated than just counting substrings. You see, it says it counts the number of non-overlapping occurrences. So I really think that the notion of non-overlapping occurrences of empty string is weird. It's not really well defined, right? What does it mean for one empty string and another empty string inside of empty string to overlap one another? Well, for example, if you count A, count ABA, you might think that the answer is 2 because there are 2 ABAs here, but in fact the answer is 1 because those 2 overlap. Okay, so it's a bit complicated interface, and then complicating interfaces, of course, as Python says, in the face of ambiguity, refuse the temptation to guess. So you might guess that the caller really wants the answer 1, but raising an exception, I think would be clear. Of course, the reason why Python doesn't do this because all those string functions are really elementary and try to do the right thing even for beginners who don't really know much about exceptions and such things. But in some cases, they are really too smart for their own good.
Yeah.
Of course, there are many other interesting things. For example, I think they have fixed this.
I love when you show some.
What do you think? Yes. In some, I think in some versions of Python, this would give you this. It would split a string into characters. Some people said that it really doesn't make sense. It makes exactly the same kind of sense as this count, because if you call it with an empty string, you can say I see an empty string here between A and B, and I see an empty string between B and C, and if you split it on all these empty strings, then you can get all 3 of those strings. But really, it's not what people want when they split strings. So it was just changed to raise value error. I think in the same spirit, this should be changed too. But of course, then Stefan's beautiful solution wouldn't work. So he would probably be opposed to it.
I can watch this back.
Okay. What else?
So we simply go through all the full four extra missions.
Yes, all 4 of them are exactly the same when you have the right predicate and the right post processor. It's very interesting.
But is this that's, I would say it's like unify everything, but makes them non-sufficient at the same time. Like, can you like, for instance, you could probably solve without predicate function more sufficient some of the mission, no?
Not really. I think it would be interesting to see some other solutions, but I think most of them really do the same thing. Let's see.
I'm not sure that for every mission you need double 4. I think for the first one you simply don't. I'm not sure.
Oh yes. In that sense, yes. But all of them, yes. I think I can make this precise. Every one of those missions need to iterate through substrings of a string. But some of them need to iterate through all the substrings, and some of them need to iterate only through substrings of some specific form. For example, starting at some specific place or having a specific length or something like this.
Yeah.
Okay. So it really makes kind of sense when you realize that to just write a function that iterates through all the substrings and then just pick up whatever you need. Of course, it's not really good in terms of complexity, because it is a quadratic complexity every time instead of, it can probably be linear on some tasks, but I don't know if there is no precondition. So you can make this solution too slow by by giving it a very long string. But
yeah, I don't say that the solution is wrong, of course.
Yes, it is just a quadratic solution. It is kind of sacrificing one level of complexity for one level of generalization. Of course, you can now you can imagine many more functions here to just use the same pattern, of course. And even more functions would be available if you didn't just return the longest substring, but if you wrote all substrings, so you can, of course, instead of this, you can write just this. Just replace return with yield, and after it, if you need really a longest substring, then you just need to say the maximal by length. And of course, if you need something else, then you just write something else. So it is kind of like a bit more general, but of course, for the four of them, the longest one is always needed.
Okay.
Okay.
Bigger together. I think this might be an interesting solution inside.
Oh yes, because it has a really non-trivial. Actually it has a very trivial algorithm, but it's very hard to prove that it works. No one has really. I think no one has really proved it, but there have been many tests from various ways of thinking about it, and it really seems that it is the right way to do it, to approach the solution. But I think it still is not actually proven. Let's see whether this one is. Yes, it is nice. It shows some interesting things that have happened when Python 3 was simplified from Python 2. Actually, Python 2 had a more general interface through which you could specify a sorting function. It is a nice lesson, I think. When you have in Python 2, you could sort some mutable, whatever, not specifying key, but specifying compare function. It was modeled after C. In C, you also write sort algorithm by parameterizing it over via a function that takes two items from iterable, and it says whether first, I'm not quite sure. No, it just answers -1 if first is less than second, 0 if equal, and 1 if first is greater than second. So it is some kind of protocol that compares two numbers or two items of any kind by just comparing in three possible ways and giving a result as a number -1, 0, or 1. Of course, it made kind of like more sense when in Python 2, of course, true was just another name for 1, and false was just another name for 0. So it made sense to, when you needed 3 items, you just added -1 as a third option. But of course, in Python 3, true and false are separate type Boolean, and makes sense in that kind. But there was another thing that Guido noticed. For example, when you need to, I don't know, compare something by length, you just say compare is compare is lambda AB, length of A is okay, compared. There was, I think CMP was the built-in function in Python 2, and then we noticed that almost all of those compare functions were just of the same form. They were always writing the same function of A and of B and comparing them. Of course, sometimes people would actually write this when they wanted reverse sort. But that was all. That was almost all of those comparing functions were always of the same type, where they always got 2 arguments, applied the same type function or transformation to both of them, and then compare the results whether in proper way or in opposite way. And we said, what if I get rid of this CMP parameter and instead of it just specify the key? It would be easier to write. For example, here you don't even need a lambda, you just say key is length. Or as in some check.io mission, it was absolute value function, right? Sorting some numbers by absolute sorting, I think, is the name of the mission, right? Remember? Okay.
Sorry, I turned off the microphone. Yeah.
Yes. You remember absolute sorting. So it's much easier to write, and it's also much faster to execute. We were speaking before about quadratic versus linear algorithms. Here, to calculate all the keys, you need the linear algorithm. You just go through iterable and you map your key over it. And for each element, you calculate its key only once. But when you have a CMP function, it's easier to see that key of an element is calculated every time when you compare this element to every other element. So, of course, there are smart sorting algorithms which don't really compare every element to every other, so it's not really a quadratic algorithm, but it could be an n log n algorithm or something like this, just to calculate the keys. Why is it important? Because, of course, this part, this key function, can be written in Python, and you usually write it some way in some special Python function, and it is important that it executes as few times as possible. Of course, you can cache it, but it would be much easier just to specify it as a parameter to sort. Of course, after that you need to actually sort all those keys, but this is done in C, and this is done via team sort, which is a really nice and really fantastic sorting algorithm, and it is much faster than whatever you can write in Python.
But in Python 3, they just get rid of the CMP?
Because in most cases it is not needed. It is just CMP is written this way.
Yeah, but why don't they just leave 2 interface for the same sort function? I can.
Well, the same answer as the answer to the question, why didn't they leave old style classes? You see, Python had two ways of writing classes. You could write class as just another type, or you can just or you can write class as a special kind of type that derives from object. And those were really two different kinds of classes, and people were very, very confused. Why didn't they leave those signs as a wrapper? Do you remember this? Okay, why didn't they leave? Why couldn't you write print with parentheses or without parentheses? You could they could leave all those things in, but Python 3 was not really about backward compatibility. Python 3 was about simplifying the language. It is really interesting to see when people now talk about Python 3 translation. They say Python 3 is much more complicated. Yes, Python 3 is much more complicated than the Python 2 people who know what they are doing actually write. But Python 2 gives you many, many more ways to shoot yourself in the foot without actually recognizing it.
Okay.
Python 3 removed almost all of these ways simply because it could. It could throw backward compatibility to the wind and just, let's say, redesign some aspects of the language, and also because it was at that time it was obvious that Python was really good to be taught to beginners, to people who don't actually know all those things that we know, that we laugh about when we see a quadratic algorithm, when a linear algorithm would do, or something like this. But beginners don't. Beginners just see those two interfaces and they just say, okay, this one looks more familiar to me.
Yeah.
And they don't really know all they don't really have all the experience that we have that could lead them to right way to do it. So in many cases, the interfaces were changed simply to point people to the more obvious solution. Of course, so
yeah, I think they just want to leave. There is only there should be only one way.
Okay, so but of course the question remains: what if people actually need it? For example, there was another thing. There was reduce. Reduce was built in Python 2, if you remember. So you could write, and people did write. something like this, and of course in many cases you didn't really have another way of understanding it but just rewriting it as a formula. And people Guido just said, okay, we will remove reduce from the core, and people were outrageous. How can you remove it? What if people actually need it? Okay, so we will put it in a module. So now you can from functools import reduce, and it works. It is the same reduce as in Python 2, but it is removed to a module. So of course, for example, all those beginners who don't yet know about modules, they are not exposed to reduce. And it is a big win. Of course, here, this CMP problem is not something you can import from a module because it is a keyword argument to a function. You cannot. You can from future import, but it's not really from future. It must be from past or something like this. But Guido had another nice solution. He had an adapter. He had a function, or actually a class, which is a nice way to, you can give it a CMP, a compare function, and it will give you something that you can put inside key.
Awesome.
Just like when you go to, I don't know, Switzerland, and they have different types of electric sockets, then you plug in your laptop inside some adapter, and you plug that adapter inside.
Yeah.
It might be very, very interesting. I think it really shows how Python dynamicity helps here to show you the code of CMP2T. It is really marvelous in its simplicity. Do you know this, that every documentation has a source code link at the beginning? Many people don't know about it. CMP2T. What does it do? It is a function that takes my CMP, which is just some compare function, and at the spot it makes another class. It makes a new class which has only one slot, so it is just a wrapper around some object. It can be initialized with an object, and it remembers it. And what does it do? It just defines all of these operators by just calling your myCMP function. And it works. For example, if those keys are needed to be, for example, less than or equal, it just calls myCMP on their objects and sees whether what myCMP returned was 0 or -1. And in all the other cases, for example, when they need to be checked for equality, it just sees whether myCMP returns 0, and something like this.
Quick question: what is slots? I probably it's first.
Yes. So slots is a way of saving. It was actually designed as a way of saving memory, but in the meantime, people realized that it was able to do many other things. The classes in Python have the dictionaries, so of attributes. Right. So if you define a class A with nothing inside of it. It has a dictionary. Of course, it contains nothing really important, but of course, it contains all the attributes inside A. One of those attributes is, of course, dict, the reference to self, the dict itself, docstring, module, because to pickle it, you must need what module is it from, and the weak reference dictionary is a separate story. However, if you have some attribute of a class, then of course parse of A is just another way to write all this reference to a dictionary without those double underscores. It will give you this attribute. Okay, so what does it mean? It means that I can now say a little dynamically update, but not only this. This is just changing the class. You can also change the instances. You can say A1 is an A, and A2 is an A, and those are two separate objects. They have separate bars. Of course, their own dictionaries have nothing inside of them. But you can, of course, you can access A1x, and it will give you 3 because x is defined inside the class. Of course, these are descriptor methods and various other complicated things that go here. But for simple attributes, it just works. However, you can say A1z is 1. Now, A1 is a dictionary that was updated, while, of course, A2, the dictionary that still contains nothing. So it must, you see, when you have a class, its objects have attributes all by themselves. When you write people usually write something like this if they come from Java. Although there is very rarely a need to write in Python something like this, but still people write it. This is just a cargo thing. But if you do something like this, and then you say L is a list of these, for example, 100 these. I really need to. I need to specify parameters. And each of them.
Oh, you switched to Markdown again.
How does this happen?
Just. I'm not sure.
I don't know. Never mind. Each of them is a B object, and of course, each of them is separate. They are not really equal, of course. Each of them is separate memory, but not only that. Each of them has an attribute A, attribute B, and attribute C. And not each attribute has a key and a value. Each key must be stored separately. Because each of them can, for example, okay, so now, of course, this one has attributes A, B, C, and D. And all the others have only attributes A, B, C. Each of them must, if you have many objects of some class, then each of them must, all of their attributes must remember separately. Okay, because those are different objects.
Okay.
It really wastes memory. If you need, I don't know, a pair of objects, for example, you write a point in two dimensions, right? It has, for example, x and y. And there, if you have a million points, you have a million, 2 million of those coordinates. Of course, you must remember them in memory. It's necessary. But you also have 2 million more strings. 1 million of them are x, and 1 million of them are y. It's obviously not necessary if all of your instances are going to have the same attributes. And slots is the way to declare it. For example, if I define a class with slots, I say my objects are only going to have an attribute A and B. Okay.
Okay.
Now, when I C by itself has a dict, you see, it already has the descriptors for A and B. If I now make a C object and ask what are his variables, the question makes no sense.
You forgot to put variable, yeah.
Yes, vars of what? I just got a list of all variables I have defined. So vars of C1 doesn't exist because C1 does not have a dict attribute. It doesn't have a dictionary in which to store attributes. So how does it store it? In a simple storage which roughly corresponds to a list. It just puts A attribute on one place and B attribute on the second place. And it is all that it needs to. CA is 5. Okay. B is. This is all that you can set. If you try to set something else, it will just say you C object has no attribute C.
But what var
only has attributes
says? Still no dict? So where the attributes are stored for? Or you can create only one object?
they are stored inside of the class. If the class says that the slots are going to be only A and B, and this declaration
so I can store only, or I can create only one object out of this class.
No, I can create many objects. C2 is C. I can say C2A is 6. C2B is 8. It works.
C1A is still
C2.
5.
Now I can access all of these attributes, of course, and those are really different places in memory. But if I, for example, I write a point with 2 coordinates, x and y, and I make 1,000,000 points, I only need to remember 2,000,000 coordinates. I don't need to remember that every one of these points has an attribute named x and has an attribute named y. You see?
Mm-hmm.
So it's kind of like a tuple. It actually has a similar interface if you make a name tuple.
Yeah, that's in that case. Correct me if I'm wrong. The class C store information or hold information about all object that was created.
No. It depends on what you mean by information. It stores the meta information, the metadata that their attributes are only going to be A and B, and no other. So each of them does not need to remember a whole dictionary of attributes. It just needs to remember two objects, one for A and one for B.
Okay.
And it is much easier to, of course, it doesn't really save a lot of memory when you have only 2 attributes, but if you have many attributes, it can save a lot of memory because you don't need to remember all those keys. You just need to remember the values. Every other programming language works like that by default. When you in Java, when you write, I don't know Java.
Yeah, but before you show that if I store like when I create the object and like initially the dict of this object is empty in case of if all the variables was created not in int function but inside of class definition.
Okay. Yes. Yes.
Does it make sense? Yeah. So in that case, dict is empty as well. So I don't see where the optimization actually here. I see some syntax is sugar here because like it says
syntax sugar is important, but not only that. If the objects were actually meant to have no attributes, then you save no memory with slots, of course. But objects are usually meant to have some attributes and to defer on them. Of course, point is maybe a very trivial example, but any object that you can imagine, you usually need to have many instances of them, and each of those instances must have some attributes in common.
Yes.
Okay, for example, if you have a, I don't know, whatever favorite object of your object-oriented programming is, it usually has many instances, and all of these instances usually have the same attributes.
Yes.
Okay, for example, I don't know, a code object. F. Now it has various attributes. Of course, it has some standard attributes, but it also has some attributes directly referring to its properties as a code. And now every code, for every function, for every built-in method or anything that has a code object its code object has the same attributes.
Yeah.
Okay. And now all of them are not, I hope, that they are not remembered in a dictionary, right? You see?
Yeah.
Because it doesn't have dictionary attribute. It has probably, it maybe has some other method, but in Python it is purely slots. I know it even has no slots because it's probably written in C. But if you wrote the class for the code for code objects in Python, then you would say their slots are simply those ones and no other. Okay. Every code has those attributes and no other attributes.
Okay. Yeah.
So in this case, of course, this class might actually have a dict, and every instance of it might have an opportunity to pick any attribute it wanted and assign it any value it wanted. But this line says that every instance of K will actually not have a dictionary, will actually probably not even have a list of them. It will just be another reference to the same object. When I write self.k, it will be the same object as the one that was passed to it.
Okay.
Right. So there are actually almost no wrapping around it. If there are no slots here, then every instance of K would be an instance of a class having a dictionary, having a key.
Yeah,
that is
I think I understand what.
Always the same obj string, and having a value that is the actual object that we want to access. And it would waste about twice more memory.
Yeah, now I understand where
so slots are almost never needed as a feature, but they're needed as an optimization. You can always delete this line and it will work the same, but you will save memory and you will get better error messages. If you actually intend your objects to only have some attributes, you should specify it. Okay.
Yeah, that makes sense.
So if you accidentally assign something else by a typo or something, you will get an error. Okay.
Okay.
So CMP2Key, of course, why is it needed here? Because this is one of those rare cases where actually CMP is not of the same form. So this algorithm says that if you compare the numbers, fancy compare A and B, you have to ordinarily compare concatenation as concatenation of A and B and concatenation of B and A. Of course, concat is for strings only written in plus, but here, of course, A and B are integers, so you need to actually concat of A and B is string of A plus string of B, and then you have to convert it back to it. This is one of those rare cases where it would actually be easier to write it in, I don't know, PHP or JavaScript or something like that that doesn't really give you much pain about types, but you just concatenate numbers. So if you have 4 and 5, you get 345. Right. Okay. So.
Okay.
You actually need this one, and this one cannot be written in the way of key of A and key of B, because obviously key of B depends on both B and A, and key of A also depends on both A and B. So you cannot really write a key function, but you can write a CMP function. Here it is. You see, you just compare. Oh yes, didn't even need to convert them to strings because there are strings from the beginning. Oh yes. He converts them to string, right? And then attacks it with this comparing function. So etc. is not needed here and here. He only needs to compare ordinarily to integers, and it can really be written as a simple minus. I said I was actually wrong. I said -1, 0, or 1 are only values acceptable for the compare, but not really. Python only is interested whether it is 0, it is great, it is positive, or it is negative.
Yeah.
So instead of 1, you can return any positive number, and instead of -1, you can return any negative number. So if you have two ints, you can just subtract them. And then you convert that to a key, and it is one way to do it. It is, let's say, Python 2 way to do it, but you can port it to Python 3 via adapter. But in Python 3, we have actually nicer ways to do it. Why? Because we can define our comparison however we want. And it might be interesting to know that while Python has 6 comparisons, as we have seen, less than, greater than, equal, not equal, which is of course just a negation of equal, so it's not defined here. Less than or equal, and greater than or equal. For sorting is such a nice way that actually you need only one operator, and it is less than. So you don't, if you intend to sort a list of your objects, you don't need to instances of A, you only need A. So actually, the pin sort algorithm never compares in any other way, but simply whether something is strictly less than something other. So if you need to write a custom comparison, you just make another class that derives from your class. In this case, it is a string, and overrides your comparison. It is just oh, I don't think this is the problem of. I think this is the problem of check.io, right?
Yeah, this is what I said. We just released recently this one update, which fixed one bug but brings a new one. Yeah.
Okay, so you will have to fix it, of course.
Yeah, it's gonna be fixed like right after the call.
Okay, so up to that detail, I think it's understandable what this does. Now etc. is just like etc. only it has a different comparison operator for less than, and it compares actually concatenations in both directions.
Yeah.
Okay. So if I do that, the only difference from Kurosawa's solution is that I don't map etc. I map this class that I have just written, right? So those are like strings, but only they sort differently. So I just sort them and reverse them and join them. I can join them like strings because they are strings, and convert that to integers and just see what is the range between the minimum and maximum way of doing it. Of course, if I join them in this order, I will have the smallest ones at the beginning, so I will get the minimal value, and if I join the reversed way, then I will get the maximum value, and that's it. So you don't actually need CMP to key if you can write your own class, because every class has its own comparison operators, and this CMP to key is just special in that it writes the class for you.
Yeah, so basically you just use
that class yourself, and you don't need to write the five of those methods. You only need to write less than if you intend to sort.
That's interesting.
Oh yes, here is written what I have said, right? Yes, converting a into a CMP format just to convert it back to key format is just busy work. So you can just write your less than directly. Okay. Reverse Roman numerals. That is interesting. Yes. So what shall I show and not show my solution? Interesting one. Yes, I think this was. Yes, it was just like he took that solution from I think Stefan Pockmann and just reversed those two lines. He had the numbers in the upper row and Roman numerals in the lower row, and just reversed it. Of course, needed to also change some other things in the code, but it's really nice that you can just some kind of swap the lines and get the opposite conversion.
Opposite result, yeah.
But let's see more interesting solutions in clear category. Well, here's yes, this is this is the ordinary solution, just with the reverse dictionary, but for mapping all the digits. Of course, you can slash that in almost a half by remembering only the digits that are necessary for 1, 4, 5, 9, right? Everything else can be just written as an addition. So,
yeah.
Not really interesting. Okay, let's switch to the creative category. Place account. I don't think I have seen it. Okay. It is an interesting one. That is also a reversal of some solution for Roman numerals that was called count and replace.
Yeah.
It went something like this, if I remember. You have a number, and then you just say, I have that many eyes. Okay, so now you have some kind of a Roman numeral that represents them, and then you replace it. For example, you replace every 5 of these with one of these, and then you replace, I don't know, every 2 of these with one of these. You see?
Yeah.
Interesting idea. And because of the way replace works, it always replaces from the start. You will actually get a real Roman numerals in that way. Okay, so it is a really nice algorithm, and this is also nice. It's just in reverse direction. So you just count this m and multiply it with 1,000, and count the d's and multiply it with 500 and so on. But of course, you need to first re-replace those subtractive notations with additive notations, and then you just various values, how many times they
How
they
many
appear.
eyes you have here?
What? Oh, this is some kind of mathematics. Well, yes, it works. Yes, nice. So you have this string that contains all of the Roman digits in ascending order, and to calculate the value, you actually you know that it's only going to have prime factors of 5 and 2, right? So it will be either 1 or 5 or 10 or 50, or it will be only 5s and 2s in prime factorization. You just need to see what are the exponents of 5 and what is the exponent of 2. And it is easy to see that, of course, when you have something like you have indices 0, 1, 2, 4, 5, 6. So you and then you want to see how many, for example, how many 5s are there. In 1 there are no 5s. In 5 there is 1 5. In X there is 1 5. In 10, in 50 there are 2 5s because it's 25 times 2. There are 2. There are 3. There are 3. You see that this is just a division by 2. Oh, I mean division by 2 when shifting by 1, and then they just wrote it. You see what is the index of such character, you shift it by 1, and you divide it by 2. When calculating the power of 2, it's even simpler because you don't have to shift it by 1. You just divide by 2. Okay.
This is hard.
Well, it's not if you know mathematics, but of course, you just every one of those numbers, 1, 5, 10, 50, you just write as 2 to the power of something times 5 to the power of something. So 5 is just 2 to the power of 0 times 5 to the power of 1. 10 has 1, 2, and 1, 5. Okay. 50 has 1, 2, and 2 5s. 100 has 2 2s and 2 5s, and so on.
Okay.
This is just an index divided by 2, and this is just an index plus 1 divided by 2.
Okay, probably.
It's really it's just numerology. Okay. So once you have those values, of course, then you just multiply everything with its value, and no, really. Then I also need to calculate subtraction. So I sum all of the x's, but I don't really. I sum minus x's if they are less than the next one. And the next one I get the standard trick of zipping with the shift sequence. So. Okay, shall we look at another derelict battery? It is a really nice. It's just an idea that I couldn't let go because the forward Roman numerals were solved by one derelict battery, by a formatter module. It was derelict in the sense that it was used long time ago in Python for writing documentation when they were needed to convert to mail or something, some other things, some other formats. But of course, in the meantime, we have got restructured text and markdown and various other nicer forms of writing help. So it just fell to the wayside. But it was interesting. It was something like HTML renderer written in Python. It could be used to write a browser or something like that, textual browser.
You mean you mean what exactly? The enum model or what?
No, formatter. Formatter was what I used in my solution.
Oh, format. Oh yeah.
Yes. I actually, when you asked me what modules do I need, I told you if you can get your hands on this one, it would be. So actually, you get the deprecation warning now, but it still works. Built-in conversion to Roman numerals, because it needs in HTML you can say something like. No, I don't really know HTML. Ordered list type is I, right? You probably know what am I talking about.
Yeah, okay.
So when rendering this one, the browser needs to know what are the Roman numerals for 1, 2, and 3.
Okay.
Okay. So if you have enough items, it must have an algorithm for converting into Roman numerals. Okay. And it's actually encoded in this formatter. This is some other kind of derelict battery in the opposite sense. The formatter was just too long ago. Scanner is probably something that's in the future, but simply no one has time to actually document it. But it is something that is meant to replace the various solutions for tokenizing and lexing and analyzing Python code. It is all written in some big mix of functions, but it can actually be done very structurally using regex or regular expressions model. And actually, in regular expressions model for a long time already, there is a scanner class. A scanner class is something that can be instantiated with something like a dictionary. It's not actually a dictionary. It is actually an ordered dictionary, because for every let's say grammatical category, you have a name, which is just how it is called, and you have a function that processes it. Okay. So you just push it into a scanner, and it constructs a scanner for you. What can scanner do? Of course, it can scan some string. And what does scan do? It actually recognizes the regular expressions in each of from left to right, and for every expression that it recognizes, it gives you some value. How it calculates that value? By calling this function. Okay. So actually, you can.
Your name.
It is not documented, so I cannot show you the documentation, but it works kind of like this. You can always just read the source code.
Mm-hmm.
Oh yeah, I haven't.
Yeah, you can do, and then yeah, just execute this once again.
And it's in it just some lexicon, whatever it is. It is, like I said, some kind of ordered dictionary, and it constructs some very elaborate regular expression. And scan actually just goes from the beginning an infinite loop until it encounters an error or end of the string. It tries to match each of those, and for every if it matches, then it sees what the index was that it matched and calls that appropriate function, and if it gets something that's callable, calls it. So I don't know if I'll be able to actually. I'll write some trivial function. So, and I'll construct, let's say, if I encounter an A, I'm going to call an F, and if I encounter a B, I'm going to also call an F. And I'm going to construct a scanner with such device. And I'm going to use that scanner to scan a string A, B, A. Okay. And it's going to print whatever F received as an argument. It always received this kind of like object oriented. So the first argument is self, and second argument is whatever it has recognized. Of course, this can be much more complicated. It can be regular expressions or something like this. But for such usage, for this usage, these constants work. And it will also give me the rest of the characters. For example, if I wanted to scan A, B, A, C, it's going to tell me that C is not recognized. So it will give me the tail that it is not recognized. Okay. So I'm just trying. This is a nice way of asserting in Python that something is recognized totally, or that something is empty. You just assign it to an empty tuple. It works because it is a special case of assigning into a tuple. Because if you write AB is 2, 3, of course it will assign 2 to the A and 3 to the B. If you write A is 2, it will assign 2 to the A. If you write A, B is 2, it will give you a type error because it is not the same number of names and values. The same if you say, for example, something like this. Of course, it's interesting. Oh yes, this is not what I intended. I actually intended this. It is value error in each case. So if there are different number of targets and assignees, then you get a value error. So if you want to see whether something, if you want to assert that something must be empty, you just assign it to an empty list. If you empty tuple. If you assign something empty into an empty tuple, you don't receive any error because nothing is assigned. Simply it does nothing. But if you assign something that's not empty, then you will get the value error because the number of targets is 0 and the number of things that are assigned is 1. Okay. So for example, for string it also works.
Can you? I'm not sure. Is it possible to use it in the middle, like the empty?
Yes. What do you mean in the middle? I can always say
A bracket. Yeah.
Or this.
Yeah, and then B, comma B.
Yes. No, because here again, these are not the same number. These are 2 things, and this is 1 thing. You can do. I'm not sure if you can do, but I think you can do this.
Yeah.
No. Okay. Start empty tuple, so actually nothing. the contents of an empty tuple, and then you assign something. And yes, it will work. Right. Of course, this is not the same, because if I write this, I cannot assign 3 things here, because these are not 3 things, these are 2 things. Right? It must have the same structure, but you can write this. Okay. Of course.
Oh yeah.
Okay, so you can actually do what you want, but you need to use a star, because you actually want to see nothing is here, not empty tuple is here. Okay.
I think they extended in Python 3. Yeah, we were talking about it in the previous.
Yes. In Python 2 it was a lot poorer, but I still think it worked. You can not really that, but you surely could do this. Right. Okay, whatever. And now what do I do? I use the same enum as before. Now I use it to construct. Then I use it to construct a formatter or something like that. And here I use it to construct a scanner. How? So that each grammatical name or pattern or what is recognized in a string is simply the name of such an enum. So the part before the equal sign, and the function is something that is almost just like a value, but not really. It is a constant function that receives anything. It doesn't really matter what it receives. It just returns that value. So you have all those constant functions, and each of them is called every time that I encounter some kind of this in a name, and it just yields, or more precisely, gives you a list of all of those values. And when you have a list of all of those values, of course, you just sum them and you get your number. That was the Roman numeral. It is very important for this to be actually an ordered dict, because that means that, for example, this is going to be checked before this, of course, because it comes earlier. So it's actually going to check for IV before just I. Okay, so I think in my previous solution with enum, it used natural order of numbers, but here I need to have precise order in, so that I check those subtractive notations before the additive ones. Okay. Something small. We have a few minutes more.
I think yeah, we should.
No, actually, I think 15 minutes or something like that. I have. If you have any questions, or is this is going live? Do people have some questions? Or?
I think we switched the translation because of the first translation was fail a bit, so we switched to another one, and we will just share the whole video.
Okay.
Then we have. I saw the amount of viewers. There was like up to 5, and now it's 1 only, and yeah, so it goes back and forth. So some visitors just shows up and leave. And
okay.
Yeah, we just share the video and put it in a newsletter next week.
Okay, no problem. So something else. Cut sentence stuff. That's really...
small one.
You could, of course, write it very easily, but it's interesting to see that Python actually has a tool, a battery for it. It is in text wrap. module. It is called shortened, so you can just call it. You have shortened I don't know, 7 characters, and it will, of course. Why? Because it has a different notion of what is the length. In this check-out mission, it is the length before appending the 3 dots or whatever it is. But here it is just how much space do you have. I think this interpretation makes a lot, maybe a bit harder to write. So it's obvious why you chose this interpretation, but Python standard library chose this one. So if you have characters, you can actually write some space and this placeholder. You can, of course, you can customize placeholder. This, or if you need a space, or of course, you can use a Unicode 3 dots, but I can type it, and I cannot type it here. So you can, if it is short enough, of course, you will have another word in here, and of course,
it's not gonna.
Right now it's only a problem how to switch one interface to another. And what do I really have to do? Of course, I need to. At the first sight, it seemed like I would have to say that placeholder is 3 dots. But actually, it is easier to say that placeholder is the empty string. So it will just shorten it, not appending anything. And then I append 3 dots according to whether it has actually shortened. And it is nice to see that it is an interesting property of strings. Shortened. It will actually compare it with respect to length. So it will be true if it has actually shortened it, and it will be false if it has not shortened it. Why? Because if you have strings ABC and ABCD, so this one is shortened, it is also less, because the comparison works that way. It compares first characters, they're the same. Compare second characters, they are the same. Compare third characters, they are the same. And then it has reached the end of one string, and then it will just say that the longer one is the bigger, the bigger one. So of course, it would be maybe more appropriate to just say here len of shortened is less than len of original, but it's interesting to see that you can actually just write shortened is less than original, and it will also work. Okay.
Yeah.
Let's see.
I think in this mission I was asked you, it may be more efficient to just check this in the very beginning. Like, can you open your?
You mean this should not be a mathematical expression? It should be an if.
Yeah, I mean,
you can check it at the beginning because you mean yes, you can, because you have this width. So
you can check if you need a cut.
Yes, of course.
Very beginning. Yeah.
It's possible to do. It's interesting to see that there is one more parameter that you actually need to set. Some people didn't, but it doesn't pass some new test cases. Break long words must be false, because otherwise there could be some I'm not sure what is the counterexamples, but if you have a too long word at the beginning, it will just not include anything. So
you can just open an editor and remove this attribute and see which test will fall.
Editor. Of course, it is my original solution. That option should be called append to editor.
Yeah.
Yes.
Just check. Yeah.
I always mix up this run and check. Right. So if you have, for example, hi.
Yeah.
You have at the start a word that is longer than the width you actually want.
Yeah.
So in this case, the Python will still, standard library will still give you one character. It will give you whatever it can in that one character, and you suppose in this case the answer is the empty string. So it is just placeholder to large. So if the placeholder itself doesn't fit, of course, it's not doing the work. But here's the no. If I have 7. Of course.
This is.
Yes. Well, now it actually shortens a word. So, but if I say it doesn't, then it doesn't. Of course, there are many options. I don't know. Oh yeah, it's not written that way. Of course, you can always look at the documentation. Well, whatever it receives.
It's weird. Why they did that?
There are very many options, such as these very long words, but just it actually forwards a lot of them to.
Oh, they just pass those extra arguments into.
Yes, initial indent, subsequent indent, expand tabs, and so on.
That
So,
makes sense.
so you actually have a lot of ways to customize the behavior.
Oh, that's sweet.
Okay, so I think
yeah, we did a pretty long run with those code review.
Okay.
Thank you very much, Veky,
Thank you
for a lot of insights. I think after the video, we also what I was thinking maybe to make to share the video, the whole video, and maybe a short before the video, short maybe an article or like the conspect of some like insights with examples, because sometimes like we started with very good audio, but then it's become the quality down. It's somewhere in the middle, so we make the concept like.
Okay, you
thank you.
You cut it however you.
Yeah.
You
Thanks again. Have a great day.
Okay, bye.